Now we talk about the graded rings associated with the projective space. So first notice that in P1 these 2 points are the same. But in this function x square minus y, if you plug in the first point you get 0, and if you plug in the second point you get 2, and 0 is not equal to 2. So this function does not work in the projective space. So the reason for the failure of this is because this is not homogeneous. You cannot take a common factor out. So these two are equal because you multiply the first by minus 1, you get this. So therefore we want homogeneous polynomials. So more precisely what we want is this f of lambda x0 to lambda xn is equal to 0 if and only if f of x0 to xn is 0. So because in projective space Pn both these points are the same. So in Pn both these points are the same, and obviously the lambda is not 0, so lambda is in k star. So this will hold. Now this above this equation, this will hold if for all lambda in k star you have this f of lambda x0 all the way to lambda xn is equal to lambda d f of x0 to xn. So notice that this is not homogeneous polynomial, but this is homogeneous, x square minus y square, and also is homogeneous is x square minus say xy. Both of them are homogeneous of degree 2. So now you can plug in both these values. Both of these values will give you 0, because you can take this lambda d, that is minus 1 to the power of 2 outside. So the projective varieties are defined as 0 locus of some homogeneous polynomials. So critical point is that we consider homogeneous polynomials for projective varieties, and therefore we have to work in the system of graded rings. So this is natural grading d I0 all the way to I, and this is the coefficient. This coefficient lies in our closed ring K, and then you have this associated monomial, so that the sum of all these is D. So for example, in graded ring you can talk about this. Say you have x0 plus x1 square plus say x1 x2 plus say x3 cubed x0. Then you can immediately see this is degree 1, these two are of degree 2, and this is of degree 4, and all of them lie in this graded ring. So all of them lie in this graded ring. These are different gradings. So this is degree 1, this is x0 to the power of 1, degree 2, this thing, and obviously all the constants, they are degree 0. So if you add 1 plus to this, this is 1 is degree 0, this is degree 0. So you have a natural grading structure on this ring k x0 to xn. So you just write it like this, that you are adding polynomials degree wise. That is, so this entire thing 1 plus x0 plus x1 square plus x1 x2 plus x3 cube x0, all of them lie in k0 k x0 to xn. Now we talk about the homogeneous coordinate ring. So the homogeneous coordinate ring V of Pn, you write it like this: kV is kx0 to xn, and then you have I of V, where I of V is homogeneous. So same as we had the affine coordinate ring, here you have the projective coordinate ring or the homogeneous coordinate ring. Only difference is this is homogeneous. So notice that this ideal x cube y square z, this is homogeneous because you consider each element separately. So this is homogeneous of degree 1, this is homogeneous of degree 2, this is homogeneous of degree 3. So this is a homogeneous ideal. Notice that sometimes this ideal could be written like this: x3 minus y square minus z, and then just z. Now these two ideals are the same, they're just written separately. So if you just look at this ideal, you might think this is not a homogeneous ideal, but if you look closely, this ideal comes from this ideal. So this is also homogeneous because this is just derived from here. So this is also homogeneous ideal. Now we talk about the function field of this variety v. So notice that this variety v obviously comes from some function f equals to 0 which is homogeneous. So you have this variety v. This variety v is defined, as we said, projective varieties are defined as a zero locus of some homogeneous polynomial. So now we are going to define the function field. As you know, function field are always given as fractions where f and g are both homogeneous. So k of v, you can see, is just the fraction field of k of v, or more precisely these are fractions like f and f over g, where degree of f is degree of g, and g does not lie in the ideal of v. So obviously, for it to make sense, because if g lies in the ideal of v, you will have a problem because g is 0, then you have to modulo out. So this degree of f of is equal to degree of g, because for f of g, if you plug in different points in the projective space, you want this, precisely for the reason here, precisely for this reason. And this lambda d will cancel out, and you have f over g will be same as f over g. So therefore you have the same degree, because you want this lambda d to cancel out. Now we can similarly define localization at a multiplicatively closed set S of some ring R. So this is R. Now you write this S in brackets. Again you have f over g. Degree of f will be equal to degree of g, where g lies in this multiplicatively closed set. Here notice that g does not lie in ideal. Here g lies in multiplicatively closed set. So it's precisely almost the same as what we did in affine case, but here we are talking about homogeneous polynomials, and when you take fractions like this, you say degree of the numerator is equal to degree of the denominator, and say f lies in the ring R. So now we talk about regular functions. So say f of g, you set it equal to h, which lies in your fraction field right here. Now this is called regular at, say, a point p. So if this g of p is not 0, obviously the denominator should make sense. So now you can construct local rings at points. So you denote this local ring by O of Vp. So this is the local ring of regular functions at point P. So since you're calling this a local ring, it has a unique maximal ideal. So what is the maximal ideal? So the maximal ideal of this ring is precisely those functions that vanish at P. So that is, if the function is given like f by g is equal to h, this f of p would be 0. And this is denoted by this m v comma p. So you can see m is written in math frac or Gothic letters. Now because we are requiring that the functions be of the form of f by g, where degree of f is equal to degree of g, we want to avoid poles. So on the entire set V, the global sections are just constants. So say V is irreducible projective variety. So V is embedded in some projective space P of n over some closed field K. Then these global sections over V are just constants. So globally the sections are just constants. So globally you have just constants. And this is precisely because you have degree of f equals to degree of g, and both of them are homogeneous. Notice that this point 0, 0, 0, all zeros does not lie in the projective space. And you have an ideal corresponding to it. So the ideal corresponding to it is this x0 all the way to xn. So this ideal you will call the irrelevant ideal, because it corresponds to this point 0, 0, 0, which is not in our projective space. And this ideal is always removed from our consideration, because the point itself is not in the space. So therefore we call this ideal as irrelevant ideal. Now we talk about the projective Nullstellen sets. So say you are given this ring A, where K is algebraically closed. Then vanishing set of some ideal J in this ring, where J is a homogeneous ideal. Now we are talking about homogeneous ideals. So J is homogeneous ideal. So this is a null set if and only if the radical contains the irrelevant ideal. So the radical contains the ideal which corresponds to this point, which is not even in the projective space. And if the vanishing set is not null, this implies you have I v of j is equal to radical of j, just like in the affine case. So corollary of Nullstellen sets, or the reason for existence of Nullstellen sets, is precisely this correspondence. The homogeneous radical ideals of A, they contain the homogeneous prime ideals of A. But homogeneous radical ideals of A, they're in one-to-one correspondence with projective varieties, and these homogeneous ideals of A are in one-to-one correspondence with irreducible projective varieties V of P and K. So notice that this corresponds to this ring A. This corresponds to this ring A. And this V will generate this homogeneous prime ideals, and here the homogeneous radical ideals. So this is the reason for the Nullstellen sets. So everything here you can find in chapter 2 of Elementary Algebraic Geometry by Klaus Heulich. So this is a good book. If you want to see the proofs, you can go to this book.